Hello there, and welcome to this collection of notebooks and tutorials on multi-rate signal processing. This is a course offered by Professor Schuller at the University of Technology. I am Renato, the instructor for these online materials, and on this tutorial we'll talk about neural networks. So the so-called convolutional neural networks, they are like cascaded filter banks, but they have a nonlinear function at the output of each filter and a constant offset. And you can read more about convolutional neural networks here in this tutorial from the internet. The coefficients of these filter banks, or when we're talking about neural networks and we're talking about weights, so the coefficients, they are called weights. In this the so-called neural networks, they simply use a weighted sum instead of convolution. So these are, for example, in a fully connected layers or dense layers. Instead of using convolution, they are the simple neural networks. So there are many different architectures, and we are going to focus just on fully connected layers and convolutional layers. And you can read more about artificial neural network here from Wikipedia, and also on this book, An Introduction to Neural Computing. Just an example of an application. You can take a look here on this work from Stanford. And it's a nice application for image understanding. So all these types of neural networks, they use several layers of cascading. When there are more than 3 layers, they are called deep neural networks, or they're called also the deep learning. So these are very current active research areas, especially, for example, in speech recognition, image recognition. And a very popular example is the MNIST handwritten digit recognition, described here on this tutorial from Machine Learning Mastery. And the handwritten digit recognition using convolutional neural networks in Python with Keras. So we will talk more about convolutional neural networks. We will talk more about Keras and other alternatives to Keras and other libraries. So this example, as most neural network implementations, they use Python, and here it's using the library Keras, which is a library that is built on top of other libraries such as TensorFlow or Theano, that used to be used in the early days, and another is very popular, also is PyTorch. Each library has its own pros and cons. Keras is a bit easier to use, and you can achieve faster results for more simple models. But it also offers less resources to the inner code. TensorFlow and PyTorch, you can have access more easy to different parts of the mechanisms, but Keras is a great library for starting and to have fast prototyping of models and trying things out. But in this course, we're going to take a look at Keras using TensorFlow and in PyTorch. So, as we said before, there is a nonlinear function in the output of the filters in a convolutional neural network, or there is a nonlinear function also in these neurons, and they are also called the activation function, and one of them is the so-called sigmoid function. So this sigmoid function is a function that has this S shape and is given by this formula here. So it's defined by 1 divided by 1 plus e to the power of minus x. And we see that we don't have any negative values. It goes from 0 to 1. And we can also plot this function in Python. We have the sigmoid function here. So we see that it behaves like a soft limiter function. So the derivative of the sigmoid function is given here. And it's the e to the power of x divided by 1 plus x e to the power of x squared. And this is one activation function, and there are other activation functions. For example, popular ones are the hyperbolic tangent, the tanh, or the ReLU, is the rectified linear unit. And in this case, the ReLU will return x if x is greater than 0, and alpha times x if x is smaller than 0. We also have different types of ReLU depending on the value of this alpha. So this alpha can be 0, this alpha can be a predetermined slope, or it can be some value. So then we have leaky ReLU or parametric ReLU. So there are different, and we also have other activation functions. So you can see here in Keras we have here many different types of activation functions. So we have ReLU, we have sigmoid, softmax, soft sine, hyperbolic tangent, the scaled exponential, the linear unit. So depending on the application, we can choose different activation functions. In the following diagram, we'll see a 3-layer artificial neural network. And we have here, we have input layer, we have hidden layer, we have an output layer, and here we have our outputs. So here we have our weights, we have our nodes or our neurons. In this example, we are using the sigmoid functions. So the values with index 0 are often assumed to be the biases. So they're fixed values. In general, we have several outputs in our neural network. So output k is the nonlinear function of a sum given by this here. So the sum is the weighted sum from the hidden layer outputs h of j. So if we choose x0 equals to h0 equals to 1, such that we obtain a constant offset as part of the sum. We get this here. Then the output of the hidden layer, hj, is again a nonlinear function f of a sum of hj. So we see here that we have our inputs, and then there is this weight, and then we have our hidden layer, and then we have weights again, and we can have many hidden layers here, but we have our output layer, and then we have our output, and we see that the output is given by this sum, and also the output of each hidden layer is also given by this sum from the inputs, and we have these weights. So the output of our neural network depends on the weights w and the inputs x. So here we are assuming a fixed sigmoid function. So if we assemble the inputs into a vector x, which contains all the inputs, and a vector w, which contains all the weights from the hidden and the output layer, then we can express the dependency, and then we can rewrite the output k. So output 1, output 2, output 3, and so on. Output k as O k x in w. So this is the output k. So now we would like to train the network, meaning that we would like to determine the weights such that if we present the neural network with a training pattern in x, the output produces a desired value. So for instance, if we present an image with an object in it, and the output indicates that the object was there with a desired output value. Hence, we have training inputs and we have desired outputs. So we will express d of k, and these desired outputs are also called the targets. Then we now use some optimization algorithm to update the weights w to obtain the outputs O of k as close as possible to the desired outputs d of k with a given input x. So what we do is we will have our desired output. We will we'll feed the network with some input. Then we have the multiplications and summations with weights depending on the number of hidden layers, and then we will get these outputs. We want that this output is as close as possible as a desired output, and then through some optimization we will adjust the weights, and we'll keep doing this until we have that the outputs of our model is as close as possible to our desired output. For this optimization, we can use, for example, gradient descent. It's a very common optimization algorithm and all its variants in optimization, but also there are other optimization algorithms. So for the gradient descent, we start with an error function delta, even here. So this is the output k minus the desired k, and for example, one always positive error function is its square. So this is also called the loss function, and in this particular choice, this is the mean squared error. So to this error function, we can now apply the gradient descent. It is also called a stochastic gradient descent in our case of neural network training. So we have this, that the x new is equal to x old minus alpha times the gradient of x old. In our case, now it will become the w new, so the weights will be the w old minus alpha times the gradient of the error k depending on x and w old. So for the gradient nabla, we need to compute the derivative to each weight w of y of the weight vector w. So in our case, we can apply the chain rule, so that the outer derivative times the inner derivative, and after these manipulations here, we get these equations. This delta and the derivative with respect to the weights. Then we have this delta k, and here we have the derivative with the respect to the weights, and here's the output. And we can compute this inner derivative first for the output weights, and again we will use the chain rule, and finally we will get this equation 4 here. So we have these equations 2, 3, and 4. So if we now plug this result 4 into equation 3 and equation 2, we obtain the update rule for the gradient descent for the output weights. So what we're doing is we're applying the chain rule to calculate derivatives, and then we will have this update rule, that is the weight oj new is equal to the weight oj old minus alpha times delta k vectors x and w, and the derivative of this s of ok times h of j. So this update rule is telling us that the update is equal alpha times output delta times output derivative times its input hj from the hidden nodes. We observe that they only have local processing for the update, which makes it suitable for massively parallel processing, for example using a GPU or a graphics processing unit. For the hidden weights, the inner derivative of equation 3 becomes a bit more complicated. So we have here the derivative with respect of the weights, output k, then we have all these manipulations here, and we apply the chain rule, and we will finally get this equation here. And again, now we plug this result for the hidden weights 5 into equations 3 and 2, and we obtain the update rule for the gradient descent for the hidden weights. And we have this equation 6, which tells us that the update is equal to alpha times the backpropagated delta times derivative of hidden function times its input x, y. So we've seen we have all these quite complicated ways to calculate to get the update rules for our output weights, and also for the weights for the hidden units. But once we pass this, we can apply in the libraries. They have an automated way of calculating gradients and calculating this, what is called the backpropagation. So this algorithm is also called the backpropagation, and we need to do this update for each output node k. This is in principle the same rule as for the output nodes, just with its corresponding input and output. So this means that the backpropagation is just a consequence of applying the gradient descent algorithm to neural networks. And a popular alternative to the gradient descent, or let's say a refinement of gradient descent in neural networks, it is the algorithm that's called Adam. And once again, we can look at the Keras documentation, and you see that we have this available algorithm. So the stochastic gradient descent, RMS prop, Adam, Adagrad, and those are very popular algorithms, optimizers. So hence, for all nodes, we retain a local processing. So we just look at one node, call its input x of y, its output O, its weights w of y, and its desired output d. Then we obtain its output with this sum here. So sum of the weights times the inputs, and then the output is a function applied to this sum. So if it is an output node, the difference delta to the desired output d is given by O minus d. If it is a hidden node, we use the backpropagated delta from an output difference delta O, weight to the output node W, and sum for the output node SO. We have this. Then we get the local weight update given by this formula here. And this we can see in this diagram. So we have inputs, we have weights, we have the sum. In this sum, we apply a function into the sum. In this case, for example, the sigmoid. So the sigmoid is applied to the sum, and then we have the output. So the weight update during training with the output difference delta. Here we will have a Python example for the MNIST digital recognition. We are not going to go through this code completely in detail now. This is just an introduction to neural networks, and this is just to have an intuition about what's going on. So we will import our libraries. We're importing the Keras dataset, MNIST. We're importing from Keras models. We are using a sequential way of building our model. We are having dense layers. We are having a layer that's called dropout. We're not going to detail about this now. So here we are loading our data set. So we divide our data set in x train and y train, x test and y test. So we have our inputs and our targets. And here, for example, are just examples of images that are part of this data set. And we have images 28 pixels by 28 pixels, and they are handwritten digits. And our goal is that we can classify, this is a 0, this is a 1, this is a 5, this is a 4, for example. So it's very common in machine learning experiments that we set a seed for our random value, so we can make this experiment reproducible. Otherwise, the results of our experiment is highly influenced by the initial values that how we start our model. So this way we will generate the same random numbers every time. Then we also will do some reshaping. These libraries, they expect a certain shape. And also we are flattening our image. So here we have 28 by 28, and we will have one flattened vector. We are also converting, we are normalizing our inputs, that they go from the values from 0 to 255, and we are just normalizing it, so it goes from 0 to 1. We are encoding our outputs. It's what's called a one-hot encode. This is a way that we can encode our outputs. Here we are defining our model, so this is a sequential, so the layers are given in sequence, and we are using dense layers, or they are fully connected layers. So it's the same as we've seen before. So we are not using convolution layers, we are using fully connected layers, and we are using the activation we are choosing to be the value. And for the last layer here, we are using a softmax. So softmax is usually used when we have this classification with so we want to classify 9 different digits. So we have 9 different possibilities, and we will use this softmax activation. And our loss is the categorical cross entropy, also used in this kind of problems. Now, after we define our model, we will compile, and then we'll have our model, and then we will fit the model. It's called we are training. So we give the input, we give the target for the training. This is for the validation. So after the model is trained, it will also validate and evaluate how the model performs. And we define some hyperparameters, so there's things called epochs, batch size. We're not going in detail now, but we will explain this later. And then we evaluate our model, and we will have our accuracy, we will have our validation accuracy, we will have our losses, and with that we will see if the model is performing well, if we need to adjust some hyperparameters. And here is just an example. So our model is trained, and then we will try it out. So we will have, for example, we take one sample from our data set. It's this image here, and then we predict. So the prediction we call model predict classes, and then the prediction is 2. So it was a good prediction because it does look like a 2. So our model predicted correctly. So we have here our sample, and then we pass to the model predict classes, and then we have sample, and then we have the prediction. So this is just one kind of classification problem, and we used Keras. So these are all the procedures that we need to take for this model to train and then to evaluate. We will go on detail later on about different parts here, but this was just to show you a general overview of an application example. We will now take a look at the convolutional neural networks. It has a different architecture and different idea behind it. So in convolutional neural networks, each layer basically consists of filter banks where fixed bias terms are added to each output and the result is passed through a nonlinearity. The filters are called the receptive fields, in analogy to the processing, for example, in the retina of the eye. The filter coefficients and bias terms are then optimized according to a target function and a loss function, which computes the distance to the target function. Let's take a look at Python Keras convolutional neural network example. So most of neural network development is done in Python. It has very powerful libraries for it. For example, Keras, Theano, that used to be very popular, but nowadays it's not so popular anymore. I'm not sure if they are still developing it or if it's already deprecated. But we have TensorFlow and PyTorch. So here you can read more about Keras. In our example, we want to detect a signal in a sequence. In this case, we want to detect a ramp that is produced by this Python function here. We want to use a convolutional neural network to detect this ramp. So in a Keras example, first we will define our input data and our desired output. It's called the target. For the input, we will prepend and append a few zeros to the ramp function, such that the goal is that the neural network has to find the position of the ramp. So here we have our ramp. We have 9 zeros before, 9 zeros after, and our ramp has 5 numbers, so we have a total of 23 numbers. So Keras expects a certain shape, and we need to expand some dimensions so to prepare that our input has these expected dimensions. And the dimensions of the Keras that Keras expects is an input with the shape that is given by the batch, the length, and the number of channels. So batch here is the number of training examples. In our case, we have just 1, so our batch is equals to 1. The length is the length of our signal, so here we have our signal has 23 numbers, and channels are the channels of our data. For example, it can be stereo, so we would have 2 channels. It could be RGB, we would have 3 channels, but here we only have 1 channel. So the target signal will have the same size in this case, because we use a causal network that returns the same number of samples at the output as the input, and we will set up our target containing all zeros except for a 1 at the time of the detecting the pattern. So we will detect the signal at its end. So we will detect the ramp at its end. So we have here zeros, and then we are having 1 at this position. So we will input this. So we have zeros, then we have a ramp, and then we have zeros, and the target is just a 1 when the signal ends. We also need to change the dimensions, and then we will start setting up our network model. So we will use sequential, then we will add a convolutional layer. This is how we do it. We define a model, sequential, and we add this convolution 1D. So we will have 1 filter. The size of this filter is equal to 8. Stride is equal to 1. We will use causal, as before. We will choose linear activation, and we will not use a bias. We will initialize our weights using the Glorot uniform initializer, and we need to pass the input shape. So the input shape is a vector 23 and 1. So a filter here is used to detect a pattern. It will be similar to a matched filter that we've seen in our lecture Advanced Digital Signal Processing, in lecture 13, that you can find in our website. So the kernel size here is the size of our filter's impulse response. So here it can detect patterns of length of 8 samples. Strides here means that there is no downsampling of the signal. A padding causal means that there is zero padding of kernel size -1 zeros before the beginning of our signal. So the activation is linear means that there is no nonlinearity after the sum. So we are not using a sigmoid or hyperbolic tangent. We are not using a nonlinearity. Bias equals to false means that the bias is 0. And for the random initialization of our weights, we are using this Glorot uniform. And the input stage is the size of the signal at the layer's input. So then we need to compile the model and specify the used error function and the optimizer. So we defined our model here, and then we need to compile and we need to specify the error function. So it's called the loss function, and here we are going to use the mean absolute error, and we will use the optimizer called ADAM. So loss here is the error function, in our case the mean absolute error between the network outputs and the target. The optimizer is the optimization function to use to obtain the best weights. And here we are going to use ADA. So after we compile the model, we specify the loss function, we specify the optimizer, then we can train the model using fit, and then we give the input, the target, and then we give the number of epochs and the batch size. So epochs is the number of iterations the optimizer will use, and batch size is the number of examples that we will have. In our case here is just one, but the batch size determines how the update of the weights will take place, and the epochs is the number that it goes through. So if we have, for example, we could have two batches. So we have 2 examples in our data set, and then we could set, for example, the batch size equals to 1 or the batch size equal to 2, and the epochs is how many times we will go through all the data set. So if we set the epoch equals to 1, we'll just have 1 iteration. So if we set it to 2, then it will go to the first input, the second input, and then it will do it again. So it's the number of iterations that goes through all the data inside the data set. So after the optimization finished, we can use our model for prediction. Here we want to detect the signal. So usually a separate test signal is used that is different from the training signal, but we're just giving here a very simple example, not going into the detail. So there are much more than what is written here about batch size, about the epoch. So we will just use the same input for testing. So here we are making a prediction. We can also read the resulting weights using this. So the first index of refers to the layer. Here we only have one layer, so we have the index 0. Then the next index refers to the input dimension, the next to the output dimension. So here we have only one output neuron, so the index is 0, and finally the channel index also is 0. So we have our filter weights. We get the weights here, and we get here W of 0, and then we have this way we get our future weights, and we can also save these weights for future use. So there are many ways on how to save. We can save the full model, we can save that includes all the definitions. We can save just the weights. So depending on your application, you can save different weight. Here we'll just save the weights using pickle. Now we can plot the output of the neural network, the weights and the input, using this part here. So when we put everything together, you can see the Professor Schuller example code in Keras simple ConvNet is a simple program that uses a convolutional neural network to obtain a matched filter. So, and we will detect the signal. So we start by importing all the libraries. We are going to use Keras and import the sequential model. We will import layers like the dense layer. We have activation. We have a convolution layer. So in this case, we are not going to use all of them. We're just important for future use. Then we have this function that will generate some artificial data in a NumPy array. So this is where we have our ramp. We will use we'll make it a unit L2 norm, so we are normalizing here this command. Then we will reshape, so it's in the shape that Keras expect. So from here we have our input signal x, which is a ramp function already shaped for how Keras expect. Here we will have our target function, which is a 1, detecting the signal at its end. And then we also reshape for Keras, and then it will return. Next, we have a function to generate the model. So we discussed this before. So we have here our convolutional layer with all these parameters. We define our loss function, the optimizer we're going to use. We compile and we get a compiled model. So for example, here just so we can see, we have generate data. So we have our input and our target. So the final shape is 123.1 for the input and 123.1 for the target. So we have the same shape. Then we have our model using this generate model. Then we train using 5,000 epochs. We evaluate, and then we will make predictions. Then we get our weights. So here the model is training and it's computing the loss, and we see that the loss is going down, down until it to go through all these epochs we define, and we see that the loss is much smaller than when it started. So here we have our predictions. We can save our weights, and here we have a plot. So after the 5,000 iterations of the optimization, we have here, this was our input signal. This is the weights, and this is the neural network output. So remember, we had a 1 at the position 16, so at the end of our input ramp, and we have here our network output. Oh, you can also compare these weights and the plot to the match filter, which we saw to detect, it's used to detect a signal with a maximum possible signal to noise ratio on lecture 13 on advanced signal processing. And we see that in the matched filter case, the weight should be the signal to detect, but time reversed. So here is a reverse ramp function. So this should be we can see like this is our weights for the meshed filter, and we had the input signal. Here was the ramp, a bit different than what we used here. And the thing is because we specified a target function which has only a very narrow peak, and this is what we observe at the output of the convolutional neural network. So this may not have a maximum signal noise ratio, but a more narrow peak at detection, which enables a more precise location of our pattern. It's interesting to see that even though it's called a convolutional neural network, a lot of libraries, they don't calculate the convolution, they calculate the correlation, the cross correlation, which can be seen as a convolution but without the reversed impulse response, so without the reversed weights. So in future examples, when we are seeing convolutional neural networks as filter banks, we need to take into consideration what's the impulse response, how to read out the impulse response from the weights, but this is another topic. Before we use Keras on top of TensorFlow, and now we are going to use PyTorch with the same example. So with PyTorch we have more control of the neural network structure, and here is how we do it. So now we import PyTorch libraries. Here the generate dummy data is the same as before. We just need to change here the dimensions of the inputs and outputs according to what PyTorch expects, not with what Keras expects. Here we need to convert the inputs and outputs from NumPy to Torch, which is this data structure used by PyTorch. This is what we are doing here. Then we will generate our model. We are using this way here, sequential, and we are defining our convolution layer with one channel as input, one channel as output, kernel size, stripe, padding, which here is kernel size -1. We are not using bias, we are not adding an activation function. We are using this time the mean squared error loss. Before we used for Keras the mean absolute error. This time we are using the mean squared error. We are using the Adam optimizer, and here, so this we have our model, we have our optimizer. This is how we train our model. So we have the predictions model of X, loss, we calculate the loss function between the predicted and the desired, and then here we just print the loss. It's computed here. Then we need this thing here to the zero grad. There's a way in PyTorch to adjust the gradient. No, we are not going into detail here what this is doing. This is the backward. It is also necessary in PyTorch, and then optimizer step. So we will see this in many PyTorch models, and you can read on the PyTorch documentation what exactly these things are doing. And then we will have our predictions, we have our weights, we can also save our weights, and here we are plotting the output of the neural network, the weights, and we observe that we have very similar results with the Keras. So basically we just try to reproduce the same example, but using PyTorch instead of Keras. As I mentioned before, instead of a convolution, many libraries they use the cross correlation. So we can see here in PyTorch documentation, we have the convolution 1D, and here we have this cross correlation operator, and it's not a proper convolution. Just some details that we need to have in mind depending on our application. In audio processing, the Conv1D layer is useful when the entire audio signal is in memory. Then the convolution can be seen as shifting the time-reversed impulse response, the weight, along the audio signal to produce the output of the convolution. But when we would like to do real-time audio processing, the audio signal arrives block by block from the sound card, and we should process them as they arrive. This can be seen as shifting the audio signal along the time-reversed impulse response, the weight. We can implement this using a dense neural network layer, or fully connected layer, using a Keras dense layer. This layer has different definitions for the weights and the input, hence we need to translate them for this layer. The dense layer basically implements a matrix multiplication, where the input signal is a row vector from the left, and the matrix from the right contains the weights. In our case, this matrix is a column vector. So first, let's look at the weights. So the weights, they don't have the channel dimension, hence we need to remove it. Then we need to apply the time reversal from the convolution, and we can do this using this flip. So here it's very important to understand if the library is giving back the convolution as time or a cross correlation, and then we need to see if we must time reverse or not. And then we can set up a dense neural network model, and we can use, instead of the convolution, we're using a dense, and then we have linear activation, BS equals to false. We test the input shape, and we have here just one unit. And then finally we need to transpose the input to be a row vector. Then we can loop over the signal. So here it still comes from the signal in memory, but it could also come from the sound card. So we're just simulating that the signal is coming from the sound card, and we will loop over the signal. And this is what we're going to do in this example. So it's a simple program to implement a convolutional neural network using a dense network for real-time audio applications. So here we are again importing our libraries. We will open the weights. We'll open the file containing the weights that we used before. So we see that the weights have this shape here. Now we need to convert the weights from the convolutional layer to a dense layer. So we are removing the channel dimension for these weights, and this is what we are doing here. So in this case, we don't need to do flipping the impulse response dimension from the convolution layer, because the convolution layer is already giving us the flipped weights. So now we build our model using this equation, and we are using a dense layer, fully connected layer. Here is the same old generate dummy data, so we are generating our inputs and our outputs. Here we are transposing the signal for the dense layer. to obtain row vector to be multiplied from the left to the weight vector in the dense. Here we will loop over the entire signal in signal steps until the end. And in each step we try to decode. And this is what we are doing. And we see again that the output of our neural network is very similar to the previous that we had here. Using the convolution, now we are using this dense, fully connected layers. So we are implementing a convolutional neural network using a dense network. This is our last example. We are going to look at real-time online implementation of convolutional neural networks. So for a Keras convolutional network, it is assumed that the entire data is already in memory, but in real time, for online processing, for instance, for real-time audio or for wireless processing, it needs to be processed as the data arrives, each sample, or block-wise, when we have blocks of samples available to us. Instead of the ConvNet sliding the filter along the samples, here we slide the samples along the filter implemented using a dense net. For that, we need to convert the weights data format. For our Conv1D layer, the weights, they have a certain format. It's an array of an array. 0 is the filter weights, 1 is bias for the first layer, and then we have filter length, channels or subbands in previous layer, and neurons or filters in this layer. So the weight format for our desired dense layer is weights and bias, but then we have the total weights, which is the filter weights times the channel, subbands or neurons in previous layer, time reversed, and then the neurons in this layer. So we also need to observe that the convolution is a correlation with flipped coefficients. So we can see what our libraries are doing, if they're performing a real convolution, if they're performing correlation, and then we can decide if we need to reverse the weights, or in case we can also flip the input signal instead. So here, the weight conversion from convolution 1D to dense is mainly a dimensionality reduction. Here, so the signal is input into a shifting buffer, so that it appears to be flipped in time, meaning that the latest sample appears at index 0, and this is what we are doing here. So this slide buffer contains a one sample up. So this is our signal block. This is dimension 1, and here is 0, -1. So this is we are putting our signal input into a shifting buffer, and then flip the signal. And since the newest values appear at the lowest index E, we have this here, our signal block. So let's take a look in our example that reads the weights from a previous trained network, and this program will implement a convolutional neural network for an analysis filter bank using a Keras dense net for real-time audio or wireless processing. So as we said before, for a Keras convolution network, it is assumed that the entire data is already in memory, but in real-time processing, it needs to be processed as it arrives, or sample-based or block-based. And then instead of the convolutional network sliding the filter along the samples, here we slide the samples along the filter, implemented using MNIST. One more time, we import our libraries, we define the filter length to 8, here we generate our model. We're having a dense layer. Before, here we are generating our data. So we have X is the ramp, and then we are taking it unit also normalize this. Here we are loading the previous saved weights. Then we need to convert the dense layer, the shape as expected. Here we are flipping the weights, and then we generate our model. We set the weights to the model, then we acquire the input signal as the ramp function, and then here we will initialize this sliding block buffer for the signal as the input for the dense net. And this is what we will do. And then we have this predictions buffer, and here we are simulating the samples coming sample-wise from a sound card. So we have this for loop here. The slide buffer contains one sample up. We assign current value to bottom, and then we will flip the signal. Since the newest values appears at the lowest index, and then we calculate the predictions, and we see when we plot that we have the same method output, but here we see that the weights are reversed, and here we have our input signal, and we see that we get the identical outputs as from our ConvNet, but now we get one output sample for each new input sample. That's it for this tutorial. There was a gentle introduction into neural networks and fully connected layers and convolutional neural networks, and the relationship between convolutional neural networks and filter banks, and a series of examples on how to use and implement convolutional neural networks using dense layers and so on. And this is also the end of our lecture on multirate signal processing. We also have available tutorials on advanced digital signal processing. More subjects are coming. We'll have audio coding, and we'll also have more on deep learning and machine learning for audio applications coming soon. Thank you very much, and I see you next time.